Simon, who is moderating this panel of distinguished mathematicians, who are going to tell us, to some extent, what it was like to be here at the Institute. I think everyone was, in one capacity or another. And how terrific a place it is. I myself came here for a semester years ago with the dual objectives of doing mathematics and finding women. I was in between wives at the time. Both objectives seemed reasonable. And what I discovered was that the Institute was a great place to do mathematics. And I did my best. Michael was here at that time and was a permanent member then, and kept up the place considerably. And certainly my experience was wonderful. So all these folks have great careers, had great careers, and maybe they're even greater because of the time they spent here. So they'll tell us all that. We're going to start with my old and good friend Raoul Bott, sitting on my right, about whose work I heard before I met Raoul, and it was with Samuelson on the application of Morse theory to the topology of the classical groups. And I actually went through that with some care and found it completely amazing. And it was in the category, a lot of people, mathematicians, once in a while you see something and you think, I would never have thought of that. And of course I was young, and but even still, that's whatever, I wouldn't. And it was a great application of work that had been done by building on work of Marston Morse, who had been a very important member of the Institute for many years, and was a wonderful application of that work. Raoul was, I think you were that one, Sanderson.
Yeah.
Is that correct? And then Raoul moved to Harvard in the early 60s, maybe 61 or 62 or something.
Late 50s.
Late 50s. I don't get all the dates straight. And has had a wonderful career for a number of years. So Raoul, tell us about whatever you want to tell us about.
Yeah, well, thanks first of all for inviting me and bringing me back to this beautiful place. I'm most probably maybe the prime example of somebody who was really fashioned, whose life was fashioned by the Institute. My background is unusual for the people who come here because I started out as an engineer and then became an applied mathematician in Pittsburgh. I was actually in class with John Nash. He was an undergraduate and I was in graduate school. And then when I graduated there, I had several lucky things happen. Amongst others, that Herman Baur came to visit. And he liked the work that I had done. I brought with me a problem from engineering, and it was quite famous at the time. It had to do with network synthesis, and Carnegie Tech was a wonderful place for me too, because they were starting a new program, and so they didn't know how to put good hurdles in front of people. So they were still very new at that, and a wonderful research director who immediately became interested in the problem that I had brought with me. And we solved it eventually. And that was quite a feather in my cap in the engineering world at the time, theoretical engineering. anyway, Herman Weyl came by, and I think it's thanks to the fact that he liked this work and so on, that I was then amazingly invited to come to the Institute to write a book on network theory. So, of course, the moment I got here, I saw all these marvelous mathematicians and this whole new world. I really didn't want to write a book on anything. And I showed up to, Marston Morse was at that time in charge of the postdocs, and I went to his office and sort of timidly asked, do I really have to write this book? And he didn't hesitate for a moment. He said, of course not. He said, here you do what you like to do. And so then I did what I liked to do. I was married already, so I didn't got more time for mathematics. But the amazing thing was that, so what really happened was that I got my graduate education in mathematics as a member of the Institute. I already had a PhD. And the Institute and all my friends, they were very supportive. I was a bit scared to go to the university because the graduate students soon saw through my career. And they could see that I was really a very poorly educated mathematician. But all in all, those were wonderful years. But I didn't write a single paper. I was just learning to a large extent. It was an exciting year anyway. The Herman Weyl was running a seminar on the de Rham theory, and George de Rham himself was lecturing in Kodaira. And these were things that somehow fitted into the point of view of my electrical network theory anyway. So this was a wonderful combination of things. I also was very lucky to have a good friend of my age, so Ernst Specker, a student of Hans Hopf, an excellent topologist, and he taught me the subject essentially. And I was a rather impetuous young man, so I kept bringing him conjectures, and after a while he would find me if he could disprove my conjecture within 5 minutes. So you see, at the end of the year, suddenly I got this amazing phone call from Marston Morse. He said, how would you like to stay another year? You see, I'd done nothing really. I'd just been learning things. Still, he had faith in me, I guess, and he said, do you want to stay another year? Of course. He says, do you need a raise? And I said, oh no. Because I was being paid $300 a month, which was a princely salary at the time. My wife took a view of that decision. But I was so surprised that I could stay another year. And so the second year I started to do more constructive work. But there's no question that my whole career would have been completely different if I had not had this remarkable opportunity of participating in a place that is so single-mindedly honest in a way, so single-mindedly determined to let your own imagination flourish. I heard Mark Oresky saying just last night over dinner that Stravinsky once said, there's nothing more terrifying than a blank page of paper. And of course, I had those feelings too, you know. I remember after Marston Morse set me free, so to speak, the question of what should I do? I mean, this vast tapestry of But there was inspiration both from the university and from here that really kept me going. So that was, I don't know if I'm speaking too long.
No.
You should have a clock or something. Because that was my first experience with it here at the Institute. That sort of started me off on being a mathematician. And a few years later, in '55, this was in '49, by the way, I can't help mentioning that our lodging situation was pretty primitive in those days. We had to stoke the stoves, we had these old barracks in which there was a furnace, you were given a supply of coal and you had to keep the thing going. And if you forgot or about it, then you would be very cold in the morning. But then, I'm glad to say that I came back in '54, and there again, I learned a completely new part of mathematics. That was the time when I met my two colleagues here. And Serre, and my private tutor was Jean-Pierre Serre, and he would say, if I couldn't follow this, he said, poor boy. But he was a wonderful teacher, and it was also he didn't fine me, but he would say, poor boy. Well, I think I've taken up enough time, and hope convinced those of you that, at least for some people, this is an absolutely marvelous place.
What we're going to do, by the way, is each of the panelists is going to say a few words, or more than a few words. I think that was perfect. And then there'll be some general discussion, and anyone who feels he hasn't had a chance to finish his story will have another shot at it. So our next speaker will be Fritz Herzberg, who in my youth had a certain mythical quality. I hadn't met him, but I would always hear him referred to in almost reverential tones, in particular by people who actually knew him, which I didn't. When I finally did meet him, I didn't know what to expect, except I was quite awed at the prospect. But in fact, he turned out to be totally charming, wonderful, happy, big smile, very welcoming, and not at all what I feared. Herzberg, of course, was a marvelous mathematician, and in his one of his most famous, if not his most famous piece of work, I don't know how you measure these things, but in any event, his work on the Riemann-Roch theorem, which was a great generalization of a classical theorem, really set the stage for a great deal of work which was done in the subsequent 20, 30 years. I don't know what's been going on. Certainly, Michael Tia and his singer followed along and produced the index theorem and all that's followed from that. So, in addition to being mythical and charming, Fritz was a tremendous influence on mathematics. So, he'll tell us.
Well, thank you very much. I feel very flattered to be here and to talk about the influence of the Institute on my career. While my wife and I are happy to be in Princeton again. We spent 4 academic years here, 1952 to 54 at the Institute, 1955 to 56 at the university, and then 1959 to 60 again at the Institute. There were many short visits in later years. Therefore, we feel like coming home. My first papers written at the Institute appeared in June-July 1953, 10 months after my arrival, and contained already the signature theorem involving the Pontryagin characteristic classes of a manifold, about which I knew nothing when I arrived. The first Institute paper is number 4 in my collected papers, published by Springer Verlag in 1987. And in these collected papers I have some comments, and there I write the following. From August 1952 to June 1954, I was in Princeton at the Institute for Advanced Study. During this time, certainly the most important period of my mathematical development, the papers 4 to 14 were written, the results of my book, New Topological Methods in Algebraic Topology, and a large portion of the results in the joint work with Armand Borel were obtained, and the theorems in the joint paper with Kodaira were proved. So the energy one has at the age of 25 alone would not have achieved this. The creative atmosphere of the Institute had to stimulate and guide this energy. It was also essential to have these 2 years only for research and without any other duties. There was so much help through discussing with many other people. Without any other duties is not quite true. My fiancé arrived in Princeton 3 months after me. We got married in a Princeton church in November 1952, and our first child, Ulrike, was born here in August 1953. The mathematical community of the Institute helped us in every way, in particular Louise Morse. Marston Morse, director of the School of Mathematics, became godfather. Well, let me come back to my arrival in Princeton. On August 18, 1952, I arrived by ship in Hoboken. D.C. Spencer, professor at Princeton University, and Newton Hawley picked me up. In Princeton, we met Kunihiko Kodaira. In spite of the heat, we began to work intensively at the Institute. I remember how excited I was when I entered Fult Hall for the first time. The, for me, elderly gentleman Spencer, 40 years old, and Kodaira, 37 years old, told me the theory of sheaves and its applications with enormous speed. When my fiancé arrived in November 1952, I was an expert in the modern theory involving the work knowing the work of Henri Catin and Jean-Pierre Serre in Paris, and of Kodaira and Spencer in Princeton. With the beginning of the Institute's fall term, Armand Borel arrived. I had met him for the first time in Zurich in 1949-50. He was a member of the Institute for the same years as I, 52-54. In 57 he became Institute professor. His famous Paris thesis appeared in the Annals of Mathematics in 1952, and through his thesis and many discussions with him, I learned characteristic classes, mainly the Chern classes, and how to consider them as elementary symmetric functions. Chern was a member of the Institute from 1943 to 45 and for the fall term 49. Much of his work on characteristic classes was done here at the Institute. It is very sad that Chern died 3 months ago. It was planned that he would participate today through a video connection. Also, Borel died not very long ago, August 2003. He would have enjoyed this day. I shall say something about our joint work this afternoon. It covers 163 pages in the American Journal of Mathematics. Understanding the Chern classes so well led to my study of the properties of the top polynomials whose importance for algebraic geometry was clear to Kodaira and Spencer and other people in Princeton. I wrote to J.A. Todd in Cambridge, England, about my definition of his polynomials using the methods of multiplicative sequences. On June 30, 1953, he answered and mentioned the following. Incidentally, I have had to revise a long-held opinion that the Princeton School of Mathematics despised anything in the nature of algorithmic ideas. Of course, I was very proud about this reaction. Now, I wanted to say many things about the life at the Institute, about the many parties, the many discussions we had during these parties, during the spring dance party, during the directors' parties, during other parties, the Christmas parties, and so on. And there were many connections also with the professors here, in particular for me with Hermann Weil. Now we are living in the Weil lane in the moment. So also I wanted to speak about our honeymoon trip, which was financed by the American Air Force. If you want to know how this was done, ask questions in the discussion. Not so much time now. So the final breakthrough came for me in the beginning of December 1953, where the proof of the generalized Riemann-Roch theorem, which was already mentioned, was completed. And so I can really say that these were formative years for my career. And you can see the effects of the Princeton stay. I was invited for 1-hour lecture at the International Congress in Amsterdam, 1954. And there is a nice story. Francesco Severi, 73 years old, was in my lecture where I explained the modern theories, including my own results and the applications of everything. And Francesco Severi said to my teacher, Heinz Hopf, during the lecture I felt already like being in paradise. And Heinz Hopf explained to me, Severi must know, he is a member of the Pontifical Academy. Well, and then my work here resulted in my inaugural lecture in the University of Münster on February 26, 1955. So this is exactly, one can say, 50 years ago, and I presented there my habilitation thesis, New Topological Methods in Algebraic Geometry. So this is, so to speak, the second doctor's degree, Habilitation, and it only contains the results found at the Institute, published as book in Springer Verlag. And as a result of all this, I received also an offer for a chair at the University of Bonn, already in July '55. But we went to Princeton again because I had accepted to be assistant professor at Princeton University from '55 to '56. Well, but I wanted to go to Bonn, and Serre, who was here, asked me, why do you go to Bonn? Who is there besides Adenauer? But I was not discouraged. I started my work in Bonn in June 1956. And from the very beginning, I thought we must have an institute like the School of Mathematics in Germany. And I immediately started, first by inviting individual visiting professors. And the first visiting professor was Nico Kuiper in 1957. And the second visiting professor was Raoul Bott in 1958. And he writes in his reminiscences in his collected papers, my class in Bonn was large and enthusiastic. He gave lectures on Morse theory, and proving in this way also that Adenauer, who did not come to the lecture, was not the only person in Bonn. And secondly, I started to introduce the annual meetings called Arbeitstagung. This began in '57. And Raoul, Michael is the founding father of this Arbeitstagung. He attended in '57. And Raoul Bott came for the Arbeitstagung '58. And in his reminiscences, collected papers, Raoul writes, "In Bonn, the Arbeitstagung brought me in contact not only with my older friends like Fritz Hirzebruch and Michael Atiyah, but introduced me to the whole European mathematical community." Yeah, I should also say a few words about the joint work with Michael Atiyah. We have 9 joint papers, and while I learned about his work with Hodge on integrals of the second kind on an algebraic variety already when I was in Princeton in '54. I visited him in Cambridge when I was in Germany during the academic year '54-'55. And we were together in Princeton in '55-'56, he at the Institute and I at the university. And Raoul was also at the Institute in this time. So we were, of course, discussing many things. And we also were, I believe, a lively part of the famous Mexico conference in the summer of 1956, the 3 of us. So we are sometimes together, Mexico and Princeton. The Arbeitstagung started, as I said, in '57. There Grothendieck gave many lectures on his Riemann-Roch theorem. And in '58, Raoul Bott lectured on his periodicity. And these 2 Arbeitstagungen, Grothendieck, Riemann-Roch, Grothendieck case theory, and Bott's periodicity were the basis of the first joint papers of Michael and myself. And we continued our work at the Institute in '59-'60, where lots of discussions with Borel and Serre helped. A basic paper on case theory was written at the Institute. Yeah, for many of the 30 Arbeitstagungen I organized, until I gave this in younger hands, Michael gave the opening lecture. This was very essential for the success of these international meetings. And this success was one of the pillars on which I based my efforts to have something in Bonn like the School of Mathematics in Princeton. Because the Arbeitstagung and the general results there impressed the committees of the German Research Association, Deutsche Forschungsgemeinschaft, like NSF in the United States. And from 1969 on, we had a special research project in Bonn financed by the Deutsche Forschungsgemeinschaft with 2 million German marks a year as budget, and which enabled us to invite approximately 40 visiting researchers, and the applications for such positions came from all over the world. And then from 1981 onwards, this research project was transformed into a Max Planck Institute, and now we have the funds to have always 12 months each year, 60 to 80 visiting mathematicians in the house. In the moment, the situation is so that we have 65 visiting research mathematicians, 16 are from Russia and 7 from the United States, 7 from Germany, 6 from France, 4 from Ukraine, 3 from Austria and 3 from Iran, and 15 other nationalities. Among the non-US citizens, there are 4 working in the United States, so the United States is well represented. And then we have also since recently a research school for graduate students, international research schools, working for a PhD at the university, but being financed by our Max Planck Institute. And right now we have 14 students of 8 nationalities. Directors, we have 4 permanent members, Gerd Faltings, Günther Hader, Yuri Manin, who just retired, and Don Sergei. And we have a good, beautiful building in the center of Bonn now. And I consider this Max Planck Institute really as a consequence of my time here at the Institute, mainly 52, 54. Because here I learned the optimal way to support mathematics. So the MPI is certainly a daughter of the Institute for Advanced Study, probably one of several daughters. Since my arrival in Bonn in 56, I thought that we must have such an institute like the School of Mathematics here at Princeton. And the Max Planck Institute for Mathematics will celebrate its 25th anniversary next year. So then I hope that a representative of this mother institute will come and celebrate with us. Thank you.
Thank you very much. Rich, well, now we'll switch to at least one younger generation, perhaps two younger generations, and get a little bit of exposure as to what's going on today at the Institute. And our first panel member is Winan it's spelled E. The entire last name is a single letter E, but I am assured that to be pronounced and you should know. So I've taken his word for it. Winan is an applied mathematician, presently at Princeton. He bounced back and forth. He got a PhD, I think, at UCLA, and then he was at Quran, and he was here at the Institute. And he perhaps was at the Institute twice. Is that correct? So 2 separate visits, and now he's at Princeton, and he does physical modeling applications, I guess, of continuous mathematics to various physical problems. So why don't you say a few words?
I sort of, my experience is a bit different. I'm sort of an outlier here. I'm an applied mathematician. So I came as a postdoc during the year when Alexander Chorin was organizing a special year on fluid mechanics. I came from the Korea Institute. And then so there was a lot of activities in that year, so the area that I was working on. So at the end of the year, I was offered a 3-year position to stay at the Institute. I guess the reason was that the Institute wanted to have some applied mathematics activities, but couldn't commit itself to hire a permanent member. So a compromise was made, so I could get this position. I immediately wanted to take this position, but there was some resistance from my wife, because I had some other tenure track positions, respectable places. You know that the Institute position is not going to lead to any kind of permanent solution. So, but still, I convinced my wife. Actually, my wife was easier to convince. Her friends were the difficult ones. They always thought it was a ridiculous idea. Anyway, I stayed. And one of the reasons that I wanted to stay is because the decision I made to come to apply math was a rather spontaneous, random decision. My training at the university was quite pure mathematics. Actually, Professor Shan came and taught us algebraic topology. So at the end, I just sort of randomly decided to come to apply math, and I really didn't know what to do in apply math. So I went to UCLA, I did what the professors did, and I went to Quran and did what everybody else was doing. But I really wasn't happy or wasn't sure whether that's really what I wanted to do. So over here, I remember telling Bob Cohn that I want to stay away from the centers. So over here, I used the time, I think very wisely, to think about what really I wanted to do. And I sort of didn't solve the problem. But I learned a lot of things which were very helpful. There was a lot of, even though what I was doing, what I was interested in, was very different from what most people here were doing, but there were a lot of activities here, especially mathematical physics, theoretical physics, that were very helpful. So I decided that microscopic physics is something that I really need to look into. So then after 2 years, so I was tenured at Quran after 2 years. So then it's very difficult to say no, not to go back to Quran. So I went back to Quran for 5 years, and then came back here at Princeton in 1999, at the other side of the golf course. By that time, I really know what I really wanted to do. So when I was offered this opportunity to organize a special year here, I really wanted to take that challenge and to sort of try to implement my vision, shall we say. Then I realized that's very difficult, because the whole process has made myself an outlier in applied mathematics. It's the kind of things I want to do. Very few people, or very few in the community, are thinking of, and most students are not trained to do that. So even though I was very excited I could do something, and I think what we did was, so this special year was on stochastic modeling that I organized together with a few other people, and with one application area we looked into is turbulence problems. But turbulence problems, of course, is what people regard that as the last unsolved problem in classical mechanics. But it's also a problem that I myself have been interested in ever since I moved to this country, but has never written a paper that I would regard as being a paper on turbulence. And I also realized, the reason that we decided to have turbulence, to choose turbulence as a subject, is that at the time, there were a few very interesting ideas on looking at problems which are simpler than the real hydrodynamic turbulence, such as turbulent convection, which is passive tracer in pollutants or something, in a turbulent velocity field, and also what is called the Berger's turbulence problems. The systematic progress were made at these problems, for these problems, so we were interested in looking at how much this could go further by the sort of systematic study. But I myself didn't see at the time already that really the real problem with turbulence could be solved by these methods. But still, it was interesting to look into how these sort of more systematic ideas could, how far they could go. The more, the area that I thought would be more productive in terms of microscopic stochastic modeling was in other areas such as chemistry, biology, materials, things like that. But we had a very difficult time finding the right people to come to this program. So one of the things I did during that special year, and the reason is that people are not trained to think in these terms, microscopic physics or stochastic terms. So one of the things I did in this year is that I taught a course together with David Kai, who had a physics PhD, about what an applied mathematician needs to know in theoretical physics. So starting from classical mechanics, and statistical mechanics, quantum mechanics. So there was a 1-year-long course, and participants were my students at the university and also junior people here at the institute who were visiting members. Because I thought that was very important. Being an applied mathematician, you not only need to do mathematics, you also need to know modeling. And we used to train amateur modelers. We used to think of modeling as being like traffic flows, really heuristic. And as a matter of fact, the very idea of modeling brings with it some sort of sense of triviality, because we're not, in some sense, everything about physics is modeling. We are writing models for physical problems. But when we use modeling in mathematics, it sort of brings a sense of triviality, because we lack the depth. So the one thing I wanted to do is to change that. We want our students to be professional modelers, to know the real physics. So that's one thing I did, which is to have this course. Now this course is becoming a standard course in Quran. Not in Princeton, unfortunately, because other reasons. So the process of being here suddenly changed my career a lot. And to see how bigger change it is, you can see that how much of I'm sort of isolated and outlier in the community it is. But I still believe this, what I'm saying is the right direction to go. It will take longer time to implement that and have more people participate in this direction, but I think this is the right direction to go. And I'll end here.
Thank you. Thank you very much. So, our second member of the younger generation is Peter Hostak, here. And he works in the field of low-dimensional topology, which is the last, I don't know, 20 years has become, 15 maybe, has become more and more exciting as the problems of these low-dimensional, 3 and 4 dimensions seem to be beginning to succumb. Peter is either at Berkeley or Columbia. I was told he's been shuttling back and forth. I think right now he's at Berkeley, but there's a struggle going on. Of some sort. In any event, he just came down from New York. Unfortunately, made it in time for the beginning of this. So, Peter, tell us about your experiences here.
Thank you very much. I'm very honored to be on this panel. It's a pleasure to be back here at the Institute. I lived 10 years of my life in Princeton. I was here as a graduate student for 5 years, and I was 3 years at the university on the other side of the tracks, and 2 years at the Institute. But the Institute has left an indelible mark on me. In the very beginning, I remember as first-year graduate students, I would take midnight walks in the Institute woods in the winter, well, the graduate students at the time, we would come work in graduate college, sort of separated from the university and not know what to do with ourselves. So we would come to the Institute for lunch. You know, friends would say, "Oh, should we go to the Institute for lunch today?" So it became the Institute for Advanced Lunch. Of course, I also came here after hours. This was, in those days, the libraries were open after hours, and you could just sort of sneak in and work there. It was a great feeling. But I was first a member here in 98, 99. I was very grateful to be able to come here. My shuttling now is very small time by comparison with what it used to be in those days. My first 3 years after graduating, I moved every 6 months, and as a postdoc, and didn't realize that this gives one the opportunity to move, but one doesn't necessarily need to take every possible opportunity to move. This was something I learned at a cost. But after I was an NSF postdoc, I was going to work with Tom Rufka at Caltech. And so I went to Caltech to work with Rufka, and he promptly left. So I was at Caltech, and I went to the Max Planck Institute, there was a special semester there, so I went there for like 2 months in Germany, and then I went here and there, and I had another year left of funding to be a postdoc at Caltech. And I thought, well, I could go back to Paradise and kind of sit there alone, or what would I rather do? Why don't I see what I might rather do? So I applied to 15 respectable places and also to the Institute. And fortunately, I didn't get any of those respectable jobs. But I did get the position at the Institute, and I thought, well, it would probably be much better to be here, where I was in great company to spend the year here instead. And besides, I didn't have to teach. So I came, and the first few months here were lost in this kind of morass of job applications, which we all have to go through, this sort of unpleasant aspect of our life that we don't so January, I began working with Zoltan Supple. We started, there was he'd been working on this problem about what, well, loosely speaking, saying that algebraic varieties are nice and that complex geometry knows something about low-dimensional topology more properly. What properties do low-dimensional properties do holomorphic curves in an algebraic surface have? So it was known that these surfaces seem to have the property that they minimize genus in their homology class. And there had been sort of an industry of people working on this, and there had been a number of sort of great results in this direction. In particular, Kronheim and Rufka had some proof that for certain classes of algebraic surfaces, the algebraic curves in them had this property. And I had been sort of working on a certain technical aspect which looked quite useful to this problem. Zoltan and I started working on this, and we worked day and night, and we both got terribly sick. We called it tongue conjecturitis. And for a month, we worked day and night and wrote this paper, which was one of probably the shortest times that has ever taken me to write a paper. And so we started collaborating after that, and it's been a wonderful collaboration for me. It's lasted for many years. Shortly before that, I had been thinking about some problems with Rufka, and in particular, sort of how gauge theory invariants transform under surgeries. And this was at a time when those gauge theory invariants weren't, this is the so-called Seiberg-Witten Floor homology. Those invariants, in fact, hadn't really been properly defined yet. So we were thinking about how they transform under surgeries, but didn't quite make so much progress. This was, I suppose, in '96. And Zoltan and I had been thinking about sort of a different invariant, which we conjectured was equivalent to the usual gauge theory invariants. And, well, Tom Rufka and Peter Kornheimer were making the gauge theory invariants be well defined. So we've been working separately for a while. And last year, when we were at the Institute, Kornheimer and Rufka had finished their construction, and Zoltan and I had understood how these gauge theory invariants transform, or not the gauge theory invariants, but another class of invariants that we had been studying transform. And it became clear that the same techniques should apply also for these Seiberg-Witten invariants. And well, Tom and I were both members of the Institute that year, and I remember he arrived. He was coming from Italy, and I called him the night that he came, and he was going to bring his family. And I called him the night before he had managed to bring the rest of his family. I said, "Can we prove the exact triangle, the surgery exact triangle for Seiberg-Witten manifolds?" And we started working on it, and well, finally at the end of by November, the four of us had written this paper, which had been sitting over our heads for years, and it was really made possible by us all being here at the Institute. Well, three of the four in this collaboration were here in Princeton. Tom and I were here, and Zoltan over at the university. And this was really possible because we were able to be here together under these lovely circumstances and really do nothing but work, which something that, well, maybe to a non-mathematician, doing nothing but work sounds like some kind of work. We're gluttons for punishment. Nothing but work. That's happened. Well, anyway, I'm just very grateful to the Institute for allowing me this opportunity. So, great.
is Sir Michael Attia, who has been both a visitor here, presumably on a number of occasions, and a permanent member. He always thought of Michael as the proverbial force of nature. When I was visiting here, he, say, dominated the place, but as far as I was concerned, he dominated the place because the area in which which I was working was related to what he was doing. Michael and his singer had, building on Fritz's work, as I said, developed the index theorem and everything that's followed from that, which has been a great amount of mathematics. Michael has been involved in all sorts of things for a very long time. He left being, to go back to England, I guess to Cambridge, to Oxford, lived at Oxford, Oxford, and where I guess he's more or less been ever since. Along the way, he became a Sir. I think you weren't Sir when I first met you, but things moved up. And we're very fortunate to have Michael with us to reminisce a little bit. So.
Well, thank you, Jim, and thank you for inviting me here to this place. I should make it clear that, I mean, I'm obviously coming last on this list. I'm the youngest one here. But I have to admit that I actually came to the Institute 50 years ago. I came in 55, just after I finished my PhD. I just got married, and of course, that formative stage in your life, the Institute had an enormous impact on me. And basically, I think I've lived off the capital I acquired when I was here. I've used Jim's financial terms, he understands these things. I came back to reinvest every now and again. I came back with further visits in 59, 67, 87, and I had 3.5 years as a faculty member around 1970. So altogether, I worked out I spent 7 academic years at the Institute. So that's a very substantial part of one's career, especially when you bear in mind that much of that is in the younger period, which is when you were at the most susceptible, most formative, and I had to admit also the most creative part of your life. So it was I had enormous, the Institute had enormous impact on me, and for all sorts of reasons. You've heard how it impacted on my colleagues, and I certainly at least as much influenced by the Institute. My first sort of contact with the Institute came in time before I arrived here, at the Amsterdam Congress in 1954, which has already been alluded to, which Fritz gave a talk. I went there as a graduate student still, and I heard the talk by Herman Weil, who was presenting the Fields Medals at that time to Sayre and Kodaira, both of whom we mentioned here. And unfortunately, he died after I came in 55. He died in Zurich. At the time, I never met him, but I did hear him talk this one address in Amsterdam, and it was it left a big impression on me. He had a marvelous poetic gift. He had literary style. He was somebody with great culture, and his speech impressed me not only for his wide coverage of mathematics, but simply the words he chose, the way he spoke. And then, of course, subsequently I read his books and his papers, and they all have this imbued with this magnificent literary style, even though he said he had to write in a language not sung by the gods of his cradle, given in English rather than German, but his command of that was much better than most people who write it, born English speakers. And, of course, Herman Weil's influence on the Institute was very profound. It permeated everything. Many people subsequently really developed ideas that he initiated. So he has always been my hero. Well, that was before I came. So when I came to the Institute, just after my PhD, I mean, I had been not exactly in the backwater, but I had been in Cambridge in England, which I mean, there were some good people there. My supervisor was Hodge, who was one of the pioneers of modern ideas in geometry, but it was many other people were old-fashioned, and there was a small group there. And so when I came to the Institute, that period, sort of really the first period of time when people moved so freely after the war, there was a string of brilliant young people here. And the people I met, well, first of all, Sayre and Kodaira were both here at the university or the institute. and there was Fritz and Raoul and his singer, all of whom I got to know at that time. We actually remember Kodaira gave these lectures at the university, which we all wanted to go to hear. Well, going to hear him was a bit of an overstatement. He sat in the front row, you could just about make out a few words. And we would go in a car, there would be a car, I'm not sure whose car it was. We would all drive down together to the university, attend the seminars, lectures 3 times a week. So, you drive regularly in the same car, you get to know people quite well. Well, this started a collaboration with all these people I met, and I written large numbers of papers with all of them. Fritz, Rao, his singer, over a 25-year period. That's a big chunk of sort of my mathematical activity. And I think the thing to emphasize also, we didn't just collaborate on work, we became close friends. And I think, it's an important part of your mathematical life is to get not only collaborators, but to form friendships. You can't really work closely with somebody if you don't like him. So, having congenial companions with whom you can work easily is very important, and I couldn't have chosen better colleagues for that to do. Our collaboration also has sort of spin-offs. Not only did we collaborate, but then our students subsequently collaborated with them. For example, Don Daguerre was my student after a while, then I went to work with Fritz, and he became his colleague, and as you heard, he's the director of the Max Planck Institute. Graham Siegel was one of my students' colleagues. He written joint papers with Rao. Dan Quillen, who got a Fields Medal, one of the Rao students, came to Oxford and still a professor at Oxford. So, not only through our own collaboration, but through that of our students, and I guess students of students, and so down to the generations, this has all percolated around the international community. When I gave you the dates of my visits to the Institute, if you were very quick off the mark, you might have seen there were some big gaps when I didn't come here. So you might have asked, why did I sort of forsake this institute, which would be the great stimulus of my life? Well, the reason is, I went to work with Rao in Harvard, I went to work with Fritz in Bonn, so we were carrying on our collaboration, but they weren't in Princeton, so I had to go and find them elsewhere. So the collaboration in Princeton continued, but now diffused around the world. There were other centres, which were sort of offshoots of the Institute, really. And of course, Fritz said, in Bonn he established his annual meeting of the Arbeitstagen, which also led to the formation of the subsequent institutes, where we met not only Fritz and Rao, but also many others whom I got to know at the Institute, like Serre would be a regular visitor. So it continued in the sort of European arena, the contact which we'd established here at the Institute. It spread around the world. And as Fritz has already indicated, the Institute served as a model for it. It was the first institute of its kind. I mean, we heard yesterday the historical references to how it sort of established itself, what its philosophy was, and so on. And they're really quite unique. There was nothing like it anywhere in the world. So, since it became obviously a great success, and people came to visit it, it stimulated some imitation institutes formed around the world. You've heard about the one in Bonn, which was very closely modelled on the Institute in Princeton, and had been a great success and still going strong. Although, when Fritz retired as one director, they had to replace him with 4 directors. I don't know what happened here at the Institute. And then next time, of course, there'll be 16 directors. Besides the Institute in Bonn, there is another one which is very closely modelled on the Institute here, which is the IHES outside Paris, which is a similar sort of structure, had a big role, lots of visitors, and it's not a coincidence, I think, that many people who spend time at the IHS end up in Princeton. Some of them are here today. So there's a lot of interchange between the institutes. They've been following, patterned on each other. There is also institutes in, the MSRI in Berkeley is a more recent, later one. And then there are ones in other countries around the world. There is the Tata Institute in Bombay, which I was at just recently with Bob Langland visiting. There are institutes in China, mainly stimulated by Yao, who was also a permanent member here for a while, but he couldn't stay still very long. He travels around founding institutes wherever he goes. and also, maybe I can mention, there is the Isaac Newton Institute in Cambridge, which Peter Goddard and I ran at the beginning, the first period of his time, and set up. And I'll maybe tell a few words about that one, because not all these institutes are clones. It's not a good idea to clone things. You need genetic diversity. You want mixes. we don't want everything to be a copy of the institute exactly the same way. So the other institutes actually don't always function in the same way. They have to reflect the particular needs of their background, their society, and so on. They're not the same exactly. But the Newton Institute is significantly different. And the reason I mention that is that it was developed in part, distinctly to be not just in pure mathematics. It was mathematics across the board. I think I'm picking up here what you said. Maybe you should go and visit the Newton Institute. You might find some fellow colleagues at different times. There are programs on different topics which cover a wide range of applications in the sciences, physics, biology, etc., which are not sort of normally covered in all other institutes. So it's a different sort of institute in that sense, and I'm obviously in favour of diversity and not having things all copied the same way. The other thing to point out about all these institutes, I think is an important factor that you mentioned here in Princeton, is that they're all essentially set up in close proximity to a good university. Separate but close. And when the institute here was founded, as you know from the lecture yesterday, the initial professors came from, some of them from Princeton University. Weber came from there. And so, at the beginning, I think there was a bit of controversy whether it was a good thing to have an institute separate from the university or not. But they solved that problem. And in Cambridge, we had a similar problem with the Newton Institute. So these institutes are all located usually next to good universities, and there is very useful interchange between them, because universities have they have graduate students, they have courses, and here you've heard a lot about, which is not coincidental, about the mutual influence on Princeton University and the institute here, and that's a thing that I think applies elsewhere. It's not a good idea to establish an institute really far away from a major university. Well, maybe it's a few final comments, sort of reflective, about sort of nature of mathematics as a whole and the role the places like the institute play. And in this, I think I'd like to include not mathematics just its pure sense, to include theoretical physics, because in the institute, don't forget, the founding fathers of the institute included people like Einstein, von Neumann, and Hermann Weyl, who were certainly not mathematicians in any narrow sense, and Einstein was a physicist. So much what I will say, I think, applies to theoretical physics. In some sense, I think mathematics, in this sense, is the most international subject you can study. It has no cultural restrictions. Language is pretty minor. You just use formulae. You don't need words even. It doesn't tie to history or politics, and so it's the most international, most really independent subject you can imagine. And actually, an interesting comment on that is that in the Soviet Union, as it was in the old days, mathematics was extremely strong. And one of the reasons it was extremely strong is that it was a safe thing to go into. If you go into anything else, you were in danger of being involved with the Communist Party or you went into mathematics, nobody cared what you were doing. And so it attracted, in particular, sons of leading members of the communist hierarchy went there to get away from their parents. And unfortunately that situation has changed now. But it is it is true that mathematics really is very sort of, and therefore you can establish it as an international centre. People come here from all over the world because there are no intellectual barriers. You can transfer your mathematics from any part of the world to any other, so long as you have the ability. The other thing about mathematics, I think, is almost unique in a sense, is that it does depend enormously on the exchange of ideas at a very formative creative stage. People think of mathematics from outside as, you write down formulas and write proofs and very complicated arguments and details. That's not the way, that's the end product, not the beginning. The beginning is a big mess. Ideas, you don't know what they are, you're not sure what you want to prove. And that's the stage where you want to discuss things with your colleagues and they help you to formulate things. And eventually you'll get some thing you might want to prove, and right at the end of the day you prove it, and that's really the very last stage, not the beginning. So it's at the creative stage that you really want to get close with other people, and that's what the Institute provided, a milieu in which you got together with people very, very early on, and then carried on after that. And I think in mathematics, you have this sort of intense kind of collaboration with people. I mean, in many other fields, I don't think that exists. You can talk about what you're doing with somebody interested, and they can talk back in a polite way. But in mathematics, you really actually are intense intellectual exchange, which goes on day and night, weeks at a time, years at a time. It's a very intense form of intellectual exchange. And of course, the other thing is true in mathematics, to a more extent than others, is the fact that it's young people that do it all. I'm sorry to say this to my older friend. I should make a digression. One of my predecessors in Oxford and Cambridge was G.H. Hardy, the famous number theorist. He was a man who liked to make provocative statements, and he said, once you pass the age of 40, you finish your mathematics and you just have to write books and do things like that. And I remember when I just as I passed the age of 40, I got invited by some university to give a lot of lectures. I thought, this is it, this is the death knell, I'm finished. Past the threshold of creativity. But anyway, it's certainly true that young people have the energy and originality which you need in mathematics to drive ahead. And therefore, at a place like this institute, it is the, with all respect to the permanent faculty of whom I was one for a child, it is the visitors who are the lifeblood of the place. They come young, in stage to be formed, they're there to receive ideas, they change, make friendships which they will take away for their whole careers. And that's what the institute has this large number of members, and that's its really primary role and its primary contribution to civilization. The role of the permanent faculty, as I see it, and I saw it when I was there, was more or less to set standards. So this is a high-level place, we don't do rubbish. You only come here if you're good, and therefore by having people here who are well-known, you attract people. They come. I knew Herman Weyl had been here, so Princeton was a good place to go. And also, of course, at the practical level, to select the visitors of the right quality. So you have to have good mathematicians who can understand what it is you're looking for. So that's the faculty can also write their papers, but I think the main function is to set the standard, select young people, and then when they're here, not to direct them what to do, not to get them to write a book, but tell them to do what you want. And Raoul told you how important that was, and you can organize a seminar, you can try and stimulate, that's fine, but don't go around telling people what they should do, let them find their own conclusions. And finally, I think when you look around these buildings and some of them around, you notice the main Fould Hall, there is this vital role played by the common room, the place where you meet and have tea and discuss. And I was here, it's usually the mathematicians who dominate those common rooms. I mean, there are a few historians lurking in the corner reading. They're the elderly ones, the young chaps who cover the floor and are busy talking, eating cakes at the same time. They eat most of the cakes. I think most of you know this, the old adage about, a mathematician, the definition of a mathematician is a machine for turning coffee into theorems. And in this building here, around here, there are magnificent coffee machines, so hopefully there are magnificent theorems emerging. I think we collectively covered a lot of ground. I was the last speaker, so I had the last word, but I approved of everything my colleagues said, and all round, all I'm saying is, here.
Well, this is a time that we're supposed to have a lively discussion of some sort or another. I'll make a couple of comments that might stimulate discussion, might not. Well, mainly one. It's interesting that of the 5 of you here, and I'm certain that this was not done exactly intentionally, 4 are sort of in the geometric arts, I would say. And when the Institute began, 75 years or so ago, I think if 5 folks had been set up here to do something similar, the distribution of mathematical backgrounds would have been different. I think that the geometrization of large parts of mathematics, I think the influence of geometry, which ebbs and flows undoubtedly over the millennia, has been quite strong in the last 30 or 40 years, and brought a lot of things together, and also the confluence of mathematics and physics, which again was obviously always very important, feeding on each other as they have over the years, but in these last 30 years have gotten even closer, so intertwined sometimes that one doesn't know. In some cases, whether to characterize someone as a mathematician. So this is a trend which a lot of you participated in, and maybe someone wants to say something about that, or anything else. So any comments on that? Michael, you might have something to say.
Well, I'll comment only on the interaction between mathematics and theoretical physics, since I've been involved with that myself for the last 25 years, I suppose. And I think it's been, as you say, it's evident in the past that there have been periods when these subjects were close together and then they've come apart. And coming back again in the last 30 years has been a sort of remarkably sort of exciting period for those of us who've seen it happening. And I have to say that I think now it's widely recognized this has been very beneficial, at least to the mathematicians. Not being physicists, I can't speak for them. But it isn't done entirely easily. You could be criticized by some people saying, why do you keep such bad company? These people, they don't prove theorems, that they're really distorting the nature of mathematics. You should actually get back to respectable stuff. And so you've got to fight that thing. And I think the physicists on the other side have to fight a similar story. They're saying, why do you hobnob with these ridiculous theoretical methods? Get back and do some real physics. So both sides have a little bit of to watch their back. Friends may stab them in the back. But got past that stage and you wear a thick armour, then it's very helpful. And it's been a tremendously exciting year. It still is. I think when I have younger people to advise, I tell them, you want to get in an exciting area? Well, you get into this, you've got the courage. It's tough, you need to know everything. But if you really want to try your hand at the sort of big stuff, get in here, we'll learn it fast. And then there are lots of potential futures. So I think it's still a very exciting field. And the Institute is a place which has, of course, great reservoirs of talent in mathematics and physics. And all this comes from the Institute. And so it's had a major impact on mathematics around the world through that interaction.
Anyone else have a comment?
Well, I think in a way the French Revolution, I mean the whole attempt of Bourbaki and a slightly vain attempt, as I said, but a grandiose attempt. But it also has a strong geometric background. And what I found so exciting during this period, which I think we all found, that very different subjects suddenly came under the same heading, that things that we were transported from one field to another, and very often, amazingly, geometry held on and was victorious. So although I suppose Bourbaki was more algebra than geometry, but the geometry shone through. And I must say that the most amazing is the geometry that we find in physics. I mean, of this whole century, the whole idea that forces suddenly became associated with shapes. You know, when I came here, of course, my hero was Einstein, and he was still alive, and I was overawed to have him around. But somehow, perversely, what I really wanted to study was topology, and so I didn't hang around here very much. And I must say the rest of the physicists also, I don't think, paid very much attention to him at the time. But then I was amazed to find that actually what I'd done around 30, 40 years later prepared me much more for collaborating with the physicists of today. But I thought it was just absolutely wonderful that the imagination that it took, for instance, to see that the invariants of physics, the charges as they are called, were suddenly transformed into geometry, to different Lie groups. And this thing has been now going on to an ever larger extent, where nowadays in the visual universe you have you have really topology reigning in some sense. As you know, we are in high dimensions supposedly, right? And to me it seems a little bit, it reminds me of the genome situation. The modern picture of the universe is that at each point the universe gives away its secrets in terms of a high dimensional topological shape, which somehow embeds in some very fundamental way the structure of the light particles, at least. So geometry has been doing very well, thank God.
Peter, you want anything to add to that?
Well, yeah, I suppose actually, this is, of course, the mathematicians all know this. We as a sort of axiomatically, we've been fed this for the past 20 years, but maybe it's worth repeating to those who are not mathematicians that just as you know, physics benefits from these ideas of geometry also, particularly low-dimensional topology, which I do, is traditionally been a sort of combinatorial subject. You draw pieces of string, and you do these changes, and this happens, which seems like what on earth should physics have to say to that? But the great tools of low-dimensional topology in the past 20 years have actually come from physics, and in particular from the physics done here at the Institute. I mentioned very briefly the Seiberg-Witten equations, but both Seiberg and Witten are faculty members in physics here. And these ideas have transformed the way low-dimensional topology is done.
Does anyone from the audience have any questions you'd like to ask any of them?
I have a comment, in fact. It won't be unexpected to Michael. He spent a week with me, and he knows when and where and how I'm likely to comment. But Weil has been mentioned, and of course, Weil is a product of a mathematical institute that preceded this one, and it was a great institute, and I'm sure was in Flexner's mind at the time, his creation of this, namely Hilbert Institute at Göttingen. And Weil himself was, of course, a great influence on those who think of geometry and physics. But Weil, of course, had many sides, and one of the great sort of moments in the basement of the Institute was a mathematical moment, but I was thumbing through old reprints, and I found inside one sheet of paper, and I'm convinced that these are the notes. I've never checked the handwriting, so I'm not absolutely sure. Weil's paper on boundary layer problems. I recently read, for some reason or other, Weil's paper on boundary layer problems. It's a beautiful paper. It's a gem of a paper. It's not well known, I think, among mathematicians, but certainly shows it himself how skilled and how inventive Weil was as a mathematician. And it was probably because of Pranttl's influence and the fact that Prantl was a close friend of Hilbert at Göttingen. And Hilbert, for example, was certainly aware of the importance of what Prantl, I remind you, was one of the great fluid mechanists of the century. And it was Hilbert was a very important person at Göttingen. Now, I think the one person at the table who actually has been concerned, I think, a good part of his life with relationally mathematics and physics is Ur. And I'm quite sort of interested in seeing whether he has a different perspective on the relation between mathematics and physics. He says he's interested in turbulence, and of course, turbulence is a subject in which one has tried to bring ready-made methods, say, from quantum field theory, and put them into play, and I understand that they've had only limited success. And I just wondered what your point of view is on the relation between mathematics and physical problems. You already indicated something, but...
It's maybe first to comment on the Prantl theory. Prantl theory of boundary layers was actually first reported in 1904 in the National Congress of Mathematicians. It's true that Weil wrote this paper on Prantl's boundary layer problem, but it didn't become very popular, unfortunately. very few people know about it. It's a very difficult problem. Still trying to think about this problem from time to time. But then, with regard to the second part of your question, which is I think what you really want to ask, I'm sort of, as you know, card-carrying applied mathematician, which means I have a rather programmatic viewpoint on a lot of things. So turbulence, that's a classical problem in every aspect, and as you suggested, methods of theoretical physics, especially quantum field theory, has been tried. But I would say not very successfully. So when I mentioned in my previous speech about these models of Berger's turbulence, simplified models of Berger's turbulence, and turbulent convection, actually that was the period of time when people started to look at this again, especially Polyakov at the university produced some methods from quantum field theory to study these problems. And indeed, some rather solid progress was made. But still, with regard to the old, hydrodynamic turbulence problem, I think it's still as hard as ever. Now, that being said, I don't think that's the end of the connection between applying physics methods to sort of say mathematical problems. I think there's a huge territory that's not explored very much, and that's other less known problems. They're becoming more and more known. Problems in polymer physics, in material science, nano, things, where really there's a lot of opportunity there, and the problems may not as hard as those. And I think they're also very profound. It's just that we haven't, the problems are less old, so they're not as known as turbulence. But I think that's really the great future. That's a place where I see practicality. Whereas if we're stuck with the turbulence problem, I don't have an idea. This is some problem that it's certainly a very well-known problem, and it's a problem that everybody should be working on. But if you don't have a good idea, I think you should stay away. But there are lots of other problems that I think are very much, perhaps as important, and perhaps there is a much better chance of doing something fundamental. I spent a lot of time last time when several years ago. I spent a lot of time here looking at chemical reactions. How do you describe in mathematically solid terms the chemical reaction process when you have solvent, water? So that's another thing that I think is very fundamental to chemistry, but mathematicians have not looked very carefully. People like Jean Wigner, for example, very good theory. The most well-known theory, which is called transition state theory, was created by him. But since then,
what's it called?
Jean Wigner.
Yes, but it's called
Transition state theory.
Transition
state theory.
transition
Yeah,
state.
so that's the basis of studying chemical reactions. But that was in the 30s, and hasn't been looked at carefully very much since then. And I think this is something it's really a mathematical issue.
Could I supplement that and perhaps ask? I think Bob somehow pointed at me. I think that I totally agree with everything being said. The potential interactions of mathematics with other fields of science. I don't want to talk about applied mathematics. I think the sciences are integrated whole are vast, and they vary from one extreme to the other. The particular areas that I've been involved with high-energy physics is one extreme point of view, where the reaction with large areas of pure mathematics happen to turn out to be extremely fruitful in those directions. But of course, that's only a minute part of the potential interaction with mathematics and other sciences, which physics is a classic example, engineering, increasingly biology and chemistry. And there are large numbers of very interesting problems. And I say, when we were at the Newton Institute, that was our function, really, to run problems which tried to bring together people from these actual disciplines who knew what the problems were, and mathematicians who might have something to contribute or might have something to learn. So it's a very large spectrum. It's hard to think of a word that really covers it. Mathematical sciences is now a popular term, but applied mathematics it always suggests particular kinds of applications.
Yeah, it's. I was yesterday much of the day at Cold Spring Harbor Laboratories in Long Island, and getting presented with various things that they're up to. And Jim Watson, who's the famous discoverer of the double helix, was sort of leading the today, and all they want to do is get more mathematicians of one sort or another to Cold Spring Harbor. 2 new buildings, what we needed, mathematical methods over here and mathematical methods over here. We need a bunch of statisticians, and we need this and we need that. So the applications of mathematics are really becoming broader and broader and more central. I mean, biology wasn't very long ago, before mathematics was largely irrelevant, I think, to what people were doing in biology. And today, it's really becoming central. So it's an old story in physics, obviously, but it's a newer story in biology. Who else has a comment, question, or disagreement? Maybe someone wants to disagree with something somebody said. Get a little. You all seem so homogeneous.
Disagree among ourselves.
Yeah, I didn't see an opening to stimulate some argument. No, the fellow next to you.
And I think that's all the questions of Michael, but I was struck by one fact. And when you compare the institute with other institutes, this institute is much broader than any of the other ones you mentioned. In other words, the other ones that you mentioned are either devoted entirely to mathematics or at best to mathematics and theoretical physics. Whereas the institute has a much broader mission, and that influences to great in history and social sciences, that influences, as you know, than that of any of the other institutions. And I find it very important, but you did mention.
Well, of course, I totally agree. We were talking here about mathematics. Well, the Institute has, of course, people with this historical subject. They cover a wide spectrum. In that sense, it's broader than the others. But I wouldn't say, I think they overlap. In places like the Newton Institute, the coverage of mathematical science is much larger than it is in the Institute here. So, they overlap. And they have people in other fields of economics and so on, not in history. So I think they're different sorts of institutions. Here you have a broad coverage across mathematics, physics, history, and so on, but not so much in the application of mathematics and other sciences. Other places there's much more of that.
I've made somewhat different comments about the institute. Well, I've been here for a long time, at the university for a long time. The last 20 years, something has changed. Before that, all the permanent members in the institute that have done the greatest work in their life but give very few lectures. So in a sense, outside do not know what they have. Also, the interaction with students was much less. So the last 20 years, something changed. Phil Griffiths gave lectures, McPherson gave lectures, and in fact, when Yao was here, gave lectures. The contact with the young kids, Mark Mathias said, be very close to a university. It's very important to give lectures to young kids. In a way, you're constantly doing research. That's a problem of the guys at Beijing, those institute there. I mean, they have, how big the Institute of Academic Sinica in Beijing? 80,000 people. They're sitting there, they're not really contact with outside.
How many did you say?
Total institute of Beijing, maybe with some of the members or families, etc. 80,000.
80,000?
Right. So see, this is really people. That's what Cultural Revolution most turbulent was in Beijing Institute, because there's nothing better to do, right? So I really felt this institute was successful to this degree was a real miracle, because they're so great. But on the other hand, go to university teaching some of the graduate students, even undergraduate, graduate students. You can find out what you're doing and contact with other guys. I think it's very important. So I felt later has been changed, this institute, like McPherson, give lectures, have students, Phil Griffiths, and Bob Langmus too. But so I really felt this institute not only just sitting in the ivory tower, not doing research what subject you want to do, contact now and then, in fact, students, I think is very important.
Yeah. Yes.
I mean, I wanted also to point out that the relationship with the university, of course, is very basic. And in Bonn, for example, my main job always remained professor in the university. So I gave courses also to beginning students. But of course, one cannot expect it from everybody. I mean, it is so that our permanent members also have some role in the university as so-called honorary professors. So they can give courses there, they can have students if they wish. And it is not possible inside the Max Planck Society to give a doctor's degree, for example, or any other kind of degree. But you can do it if you are a permanent member there by having this role in the university, and maybe give even through the Max Planck Institute a stipend to a pre-doc or postdoc, and then work with him. Yeah, so there are many lines connecting the university and the Max Planck Institute, and the Max Planck Society as a whole under one of the recent presidents wanted to make this connection with universities more systematic, and therefore they introduced the possibility to having at the Max Planck Institute so-called how are they called, Max Planck International Research Schools, and these are schools in which graduate students, international, can come and apply. Therefore, I mentioned this in the moment 14 students we have from many countries, which work often with one professor in the institute and one professor where they come from. Most speaks, they have two people who take care of them. And yeah, the need was felt that one should have good connections with the university. But one has to keep the freedom of the members maybe not to do this. Depends on the special situation. Yeah. And as far as the sciences are concerned, the Max Planck Society as a whole is very much aware of this. For example, they have founded a Max Planck Institute for Mathematics in the Sciences in Leipzig. Yeah, when the German unification took place, they wanted to be present in the other states of Germany. And so, for example, the Max Planck Institute for Mathematics in the Sciences was founded. And there also theoretical biology plays a role, and also the material science.
I just wanted to mention one thing that wasn't emphasized quite so much by the speakers. They emphasize the people who've been at the institute and have gone on to be leaders of mathematics. There's something like 70 members a year that come to the institute in mathematics, many of whom are young and in the very first stages of their career, and all of whom are really at the top of the graduating or recently graduated PhDs. And so they see each other, they meet each other, they form friendships with each other, even if they do not collaborate with mathematicians in completely different fields. And many of these people will go on to be very respectable, solid mathematicians and perhaps leading figures at the universities where they end up teaching, but perhaps may not be among the very top leaders of the subject. But yet the mathematical tastes and friendships that they formed here, I think, govern their standards in the universities where they will be later, and I think it greatly increases their value to both the universities and to mathematics as a whole.
That's a great point. No one can argue with it. Maybe we'll take one or two more questions and then wind it up. Yes.
Well, I'm not a mathematician, but one thing I don't hear, and my husband's a mathematician, and I realize that there's a special place that scientists need that's quiet, and it's an environment where you can really think and be able to really create. And that's what I think institutes are beautiful at doing. What I find interesting is that, today in other areas, just about everything has the name of a business attached to it. And the money comes from those businesses, and I'm sure the development office takes a lot of time to talk to those people here as well. But, I mean, why hasn't someone like Bill Gates come and made it so you don't have to struggle to find a dime just to keep the place running? Why wouldn't you accept that if that came? That's my question.
Do you know how to reach him?
Why doesn't he realize how important the work you're doing and take care of things like this? I don't understand why people haven't already done that.
Sure.
Microsoft has a research group of research mathematicians.
They're
It just
own.
has a different feel.
Right. And you don't want to be attached to a particular business, right? Because then you feel like you were owned.
Well, they never approached me.
Right. I just don't hear the word business at all.
The fact is, the Institute is happily, reasonably well financed. We'd like to, or they'd like to, on the board, so I hope so, find some, make it even better financed. But I would say that outreach that the Institute does, especially given that it's not a desperate outreach, it's continuous and very helpful, is, I think it serves a good purpose besides adding some money to the coffers. It creates some interaction between the community and between other people. There's a teaching aspect to it. People come onto the board, learn something about the Institute, learn something about mathematics and science, and write some checks besides. So fortunately, the Institute, as I say, is in a good position. We'd like it to be in a better position, but I think the dynamic is pretty good. Yeah.
Perhaps I could just emphasize that, Jim, and come back to a point that Raoul made, I thought, absolutely beautifully and very inspiringly. The point about he was invited to write a book, and then the first thing he was told was he didn't need to write it. Now, and how important that was for his subsequent development. The ability to have that sort of situation depends on the independence of institutions like this, because increasingly in the world at large, that is what you're not allowed to do. You are required to deliver on what you said you were going to do. It remains true of his institute that he will have that freedom. That's absolutely vital to the place. It is crucially dependent on financial independence, and therefore something we have to strengthen.
One more. Okay, no more. Thank you very, very much.